class. Welcome to another tutorial on CS575. This time we will be looking at the random walk model. So let YT denote the S&P 500 composite index, that the example we were seeing in the previous class. Then the time series plot of difference S&P composite image suggests that a suitable model for the data will be YT minus YT minus 1. So as we saw in the previous case, this differencing led us to a stationary model, a stationary data series, right? So subtracting the current series minus the lagged version of it, and the difference of these two basically leads to an error, right? We term it as a white noise. We will see more in the next slides. So equation in the previous slide can be rewritten as this. Basically I just move this particular term on the right hand side, so this minus gets plus here. This model is known as a random walk model and is widely used for non-stationary data, right? So this model basically says that my current value is the previous value plus a error, right? So this model is very widely used for a non-stationary data. Random walks typically have long period of apparent trends, right? Long period of apparent trends up or down, which can suddenly change direction unpredictably. So let us see what this line means. If you see for this particular data, right, so you can see there is apparently some trend here. So let me change the pointer color. You can see there is a trend here, again there is a trend here, there is an increasing trend, and there is a sharp decrease, right? An increasing trend, again a sharp decrease. So there is an apparent trend, right? The trend increases and suddenly there is a sharp decrease, and again there is a sharp increase. So for such kind of data, we basically use the random walk model. So we say that my current value yt is nothing but my previous value plus some error, right? So let us say we are at this particular point. This value is sum of basically the previous value and some error. Similarly, this point can be basically written as y t minus 1 is equal to y t minus 2 plus an error term. So this is how you can see basically the series has an effect on the of the previous terms that are basically coming into the model. Now how do you remove non-stationary? In the previous case we did see that we did a first order difference, right? So for the first order difference we just took at yt minus 1. So for example it will be y dash t, right? So in this case the second order difference is defined in this particular way. Right, so first order will be y dash t minus y t minus 1, right? So you can actually rewrite this. For a second order difference it will be y double dash t is equal to y dash t minus y dash t minus 1. Okay, now you can substitute this. So y dash t, basically you know it is yt minus yt minus 1, and when you substitute that you basically can come across this thing, right? This is y dash t and this is y dash t minus 1. So the second order difference basically will come out to y dash t minus twice of yt1 plus y of t minus 2, and so on it will proceed. It says that in practice it is almost never necessary to go beyond second order differences to make the series stationary. Now there is a concept of seasonal differencing. So for example, what happens if your data is seasonal? So let's say the sale of ACs or ice creams or heaters in winter, these basically represent the seasonal data, right? So with seasonal data the issue is a simple differencing may work, but it is always better to do a seasonal differencing. So let us get through this. With seasonal data which is not stationary, it is appropriate to take seasonal differences. So for example, if you take the sale of ice creams, it will be obviously very high in summers as compared to a sale in winter. So let's say if we have 4 seasons in a year, S1, S2, S3, S4, So, and you plot the graph, you may see that the sales of ice creams in summers will be increasing. So instead of doing a normal differencing with the previous season, we directly do a seasonal based differencing. Here we say that a seasonal difference is a difference between an observation and the corresponding observation from the previous year, right? So if we take April, May, June as 3 months of summer, then basically we will difference with the previous year's April, May and June data, right? So this is known as seasonal difference. So as you can see, yt is yt minus s, right, where s is the length of the season actually. So this seasonal can be anything. For example, if we see finance again is divided, a year is again divided into set of quarters, Q1, Q2, Q3, Q4. So again, if you see a seasonal pattern there, we can have a seasonal differencing. So the gap quarterly sales is an example of non-stationary seasonal data. We will again see this. So you can see here, these dots basically indicate a particular season, right? So there is a peak during a particular season and then there is a downfall, right? So this indicates that the data is non-stationary. Again, we check the ACF. So there are many values which are above the confidence intervals, right? And there is a decay in the values, a slow decay. Second thing, when we see the, okay, we are having only the ACF here. And now this is seasonal differencing, right? With seasonal differencing, you are differencing with respect to the season. So for example, the seasonality difference, the change in sales between quarters, right? So a single quarter is difference with respect to the previous quarter, right? So data of first quarter from the data of the current quarter, data of second quarter from the data of the current second quarter, in this way. So now you can see the data is not a perfectly stationary data. If I draw a mean here, so there is also an approach where you can basically do a simple differencing after doing seasonal differencing, right? So as I said, for converting to stationary, there are many methods. You need to adopt and then plot an ACF and check whether it is stationary or not. So now you see, when you do a seasonal differencing, you still have almost two values which are above this interval, and you can see this is basically lag 4, right? And we have a season of Q1, Q2, Q3, Q4. So you can see even after seasonal differencing, there is some point which is above this particular red line, showing that there is still some seasonality left here, right? There is some seasonality left. You can again, let me just clear all the ink. Just have an observation here. There is some seasonality which is still left here. All other points are below this interval, right? So for that, the series is much closer to being stationary, but more than 5% of the spikes are beyond 95, right? So seasonality is still present in the spike shown at lag 4. So you can again see this is at lag 4, the PACF, it is still above 0, right? So showing that it has significant value. The remaining non-stationary in the mean can be removed with a further first difference, right? Although the order does not matter when you apply seasonal when first order differences, it does not make any difference, but the recommended is you just apply seasonality first, right? It is recommended to do the seasonal differencing first, since sometimes the resulting series will be stationary. So you, for example, in this particular case, we see that even after applying seasonal differencing, there is some seasonality left, right? So you need to again apply a simple differencing, right? That will not do seasonal wise, you can just apply a simple differencing. So the order does not matter technically, you do simple differencing then seasonal differencing or vice versa, but it is recommended that for such data which is seasonal, you would apply the seasonal differencing first. At many times you just do a seasonal differencing, your data is automatically stationary, right? The series resulted from the first difference of seasonally difference, right? So first we applied the seasonal difference and then we applied the first difference. So now we see the time series of the plot difference at lag of 4. Season was like Q1, Q2 and 1 because simple differencing. Now you can see the data is nearly a stationary data. So almost 95% of the coefficients are within this range, only this particular. So as I said, 5% is allowed to go beyond the differences and the rest should be within this particular interval. So I think guys, that's it for this particular lecture. Have a good day.